Welcome back. Hopefully everyone has taken the second exam and is now ready to move on to our next set of topics. You can think about everything that we've learned up to this point has been our conceptual mountain that we've had to climb. And where we had to learn about central tendency, the average, we had to learn about variability, the standard deviation, we had to learn about the concept of probability, we had to learn about z-scores, and then we had to learn about this broad approach to asking research questions called null hypothesis significance testing. But now finally, we're going to learn how to calculate inferential statistics, which are numbers that we calculate for our samples that actually allow us to quickly and efficiently ask and answer research questions. And the first one we're going to start with is the one sample z-test. And so today's lecture is all about the one sample z-test, which is literally just an extension of everything that we've learned up to this point. It's a little bit of new material, but mostly I would say most of it is stuff you already know, putting it together in a new way like a recipe. So think about the one sample z-test is like a recipe to efficiently and quickly calculate a number that will allow you to ask and answer your cool research question, quickly and efficiently allow you to decide whether or not to reject or fail to reject the null hypothesis. So let's get going. So the one sample z-test is for when you have one sample. It's right there in the name. When you have one sample of quantitative data. Right, now what is quantitative data again? Well, that's when you have differences between your individuals in terms of amount, where the variable is a way that people can be different, and you're going to ask someone a question like, how much do you love dogs? How many cups of coffee do you drink in a day? So the variable, right, is going to be such that when the person gives you their answer, it's going to be a number because the people are going to be different in terms of an amount. So a quantitative variable, which gives us quantitative data. And so the one sample z-test is for quantitative data, where we're going to grab one sample of people, calculate their average, their x-bar, and then compare that to some null hypothesis population, some comparison population where we already know the population average for that comparison population, or we define that population average as something to compare our data to. And so let me give you a couple examples of research questions that we can now ask and answer using the one sample z-test. Does an early start intervention program, like let's say Head Start, which is where kids get breakfast and like enrichment type of programs, cognitive enrichment, does like an early start intervention program improve academic performance? Right, where let's say ahead of time, I already know what the average academic performance is for children across the U.S., right? So now I have my comparison null hypothesis population, and I'm going to give one sample of kids Head Start, and then I'm going to take that one sample, x-bar, and then compare that to that known population. Or here's another example. Is the current IQ in the United States really 100? Because let's say for measurement purposes, I want to make sure that when I say the average IQ, that it's this known value of 100. So I'm going to define the average in the null hypothesis population as 100, and then grab one sample of people from the US, and then compare that to that null hypothesis population where I've defined that null average as 100. This should all be sounding really familiar because this is exactly what we learned to do last time, right? It was the very last topic that we sort of left off with for our second exam. It was null hypothesis significance testing. And all a z-test is one flavor, one type of recipe you can do in sort of the null hypothesis significance testing cookbook, if you'll forgive the food metaphor. So, let's do this example about Head Start. Does an early start intervention program improve academic performance? Where I have to know ahead of time that the mean, the average for academic performance for, let's say, kids across the U.S., I know it to be 28 on some standardized assessment with a standard deviation of 12. right? So mu is 28, and the amount of variability, the standard deviation in that known population is 12. So this becomes my null hypothesis population, my comparison population, where I'm going to gather some data in hoping, as the researcher, to decide that Head Start works, and I can reject the idea that kids who get Head Start have the same amount of academic achievement as kids who don't. So, but ahead of time, I know that kids who don't get Head Start, just the general population, which then becomes my comparison null population, they have an average of 28 with a standard deviation of 12. And then I tell you, I'm going to grab a random sample of 16 students and give them Head Start, right? I'm going to get a random sample of 16 students, give them Head Start, and then they get an X bar, a sample mean of 30. And so now X bar is 30 and N equals 16, right? So let's refresh our memory of what the null hypothesis significance testing approach does. It says this. The null hypothesis would say that does early start intervention improve academic performance? No, it doesn't. That in the population, post-intervention, that's why I have mu sub pi here, post-intervention, the average is still 28. Even the kids who get Head Start, they're going to still have an average of 28. And if I happen to get a sample average above that, that's just sampling error, random error. I just randomly got something a little bit higher, not because Head Start works, right? That post-intervention, after they get the Head Start, their average is still 28, right? So the average for even kids who get Head Start is equal to 28. That becomes my null hypothesis, the one that I'm hoping to reject. And then my awesome alternative research hypothesis answers this question, does an early start intervention improve academic performance, simply answers it in the opposite way. It says, yes, academic performance will be different. Absolutely, we can change academic performance. So the mu, the average for the kids who get Head Start, is not going to be equal to 28, right? So post-intervention, that mean, that average, is not going to be equal to 28. The getting Head Start in the population is going to have some meaningful difference. So if I get something like 30, that represents a meaningful difference. Now again, these are two hypotheses that we're pitting against each other. And last time, we learned about conceptually how we would do that. And so let's remind ourselves how we would have done that. So what would I need in order to answer this question? Because which hypothesis am I going to go with? Am I going to go with the null hypothesis and be sad? Oh, Head Start doesn't work. Am I going to go with the alternative hypothesis and be happy? Yay, Head Start works. Sesame Street and breakfast for everyone, right? Well, what am I going to need to answer this question? Well, we learned last time that we're going to need a critical value or critical values if we're doing a two-tailed test. First, we set our alpha, right? This is that weird symbol for alpha. Let's say we set alpha at 0.05. Remember, you get to decide what alpha is as the researcher. You set your alpha at 0.05, and this determines the critical value. That's one way of answering this question. But also, remember, we might want to look for a p-value, which is going to be the probability of getting an average like yours, a sample average like yours, right? Something as or more extreme than, in this case, 30, because we got an X bar of 30, when you assume the null is true. That's the p-value, right? If you take a critical value approach, right, then these are going to be the values that cut off alpha, right? When you look at the x-axis, the critical on a probability density plot for the null hypothesis sampling distribution, right? When you sort of look at that density plot, oh, I have a typo here. I'm going to fix it. Sorry. When you look at that null hypothesis sampling distribution, the critical values are what cut off alpha, right? You decide that you're going to reject the null hypothesis if you find anything in the extreme tails, alpha 0.05, and then the critical values are those numbers along the x-axis that cut off alpha. If you calculate any x bars, any sample averages more extreme than the critical value, you reject that null hypothesis like the lemon hypothesis it is. But also keep in mind that most computer programs are going to spit out p-values. They take the p-value approach, right? Where you look up the probability of getting something like 30, right? And if 30 is very improbable, if your p-value is very small, then you reject the null hypothesis, right? If we decide that the p-value for 30 is very small, smaller than what? Alpha, then we reject the null hypothesis. So let's look at some pictures and refresh our memory of the null hypothesis significance testing approach. So this is my null hypothesis sampling distribution, right? For any particular question, not for this current question, but any particular question, right? Here you've got, we know that the infinite number of averages is going to be normal, right? We know that it's going to be centered on whatever the null hypothesis value is. Once we decide on an alpha, if it's a two-tailed alpha, we put out some alpha in the top tail, some alpha in the bottom tail, right? And this becomes our areas of rejection. And then whatever values cut off alpha along the x-axis becomes our critical values. So in this example that I've sketched out for you here, if I calculate 2 or 3 or 4, I'm going to reject the null. Or if I calculate -2, -3, -4, I'm going to reject the null hypothesis because it looks like my critical values are 2 and -2 because it looks like my null hypothesis average here is 0 for this example. And so then this slide shows us what the theoretical p-value would be, right? Whatever sample average you get, right, x bar, then cuts off the p-value. And so let's say I had an x bar way out here in this example. If I eyeball the x-axis, it looks like I got a sample average like of 2.6. Well, 2.6 would be in this example's area of rejection, right? So, and 2.6 would be more extreme than this critical value of 2. And then this p-value here would be smaller than alpha. So let's apply these concepts of the critical values and alpha and p-values to the example from here, right? Where I know that the population average for kids who don't get Head Start is 28. So that becomes my null hypothesis average and my population that I'm going to compare my one sample of 16 students to that got an average of 30. So let's do that. And here it is, right? So I've chosen to do a two-tailed test because I'm going to choose a non-directional test because I'm going to check in this upper tail to see if getting Head Start improves academic performance, but I'm also going to check in this lower tail to see if getting Head Start hurts academic performance. I'm going to do both, right? I'm going to do a two-tailed test. So I put 2.5% in here and 2.5% in here if I choose an alpha of 0.05. And now I calculate standard error. Right, and I go back here and refresh my memory. So how do I calculate standard error? I take the standard deviation for the known population and I divide by the square root of the sample size. Because when I grab one sample of 16 students, then I know in my comparison null hypothesis sampling distribution, each of those infinite number of samples is also going to have 16. Because then my one sample is theoretically but one of the infinite number that comes from that population. And so here, let's calculate standard error. We get 12 over the square root of 16. And where do these numbers come from? 12 is sigma, because remember, this is how we calculate standard error. And then this, so we've got 12 over the square root of 16. And so that ends up being 12 over 4. And so standard error is 3. Zooming back to this slide, you can see that I have put that on here, that alpha is 0.05, right? Standard error is 3. The null hypothesis average is 28. So this theoretical hypothetical sampling distribution of the mean is centered on 28 and has a standard error of 3. So one standard error above the mean would be 31, and two standard errors above the mean would be 34. One standard error below the mean would be 25. One standard error Another standard error below that would be 22, because that's how my infinite number of averages in a null hypothesis universe, right, on a null hypothesis sampling distribution, that's how spread out those averages would be. And so then here is where 30 would be a one sample of 30, because that was what my one sample average was, on this theoretical hypothetical distribution of an infinite number of averages. Now notice that 30 does not fall in this red area of rejection. So we're going to fail to reject the null hypothesis. And now let's look at what the p-value would be. Now the p-value is set by that average of 30. Anything above that 30 is a part of the p-value. And if you're doing a two-tailed test, your p-value gets doubled. So not only is anything above 30 a part of the p-value, but everything below that's equally far away as 30 was, in this case, looks like 26. Anything below 26 is also a part of the p-value. So this plus this is the total p. And as you can see, this yellow area is way bigger than this little red area alpha, which is what you'd expect, right? And if we look at what our two critical values are, we see we have a critical value here of 34. We have another critical value here at 22. 30 was not bigger than the critical values. It did not fall in the area of rejection, and p was greater than alpha. So we're going to fail to reject the null hypothesis. Fail to reject the null hypothesis. 30 is not far enough away from 28 to reject the null hypothesis. 30 is a perfectly probable value. It's a perfectly reasonable thing to believe. If the null is true and Head Start doesn't work, getting a sample average of 16 kids with an average of 30 is perfectly reasonable. It's a very probable thing to happen because lots of samples would be as or more extreme than 30. Failed to reject the null, and we're bummed out, right? We're bummed out that we didn't prove the null, but we're bummed out that we failed to reject it, right? We can't go on Oprah. We can't go, woohoo, look at my findings. I found cool things. You're going to go, oh, ho-hum, this program doesn't work. These kids aren't different, right? These kids are not different. So now, that was everything that we went over last time, right? All of these ideas are the things we went over last time. But now, we're going to extend our knowledge. Because having to draw these pictures all the time and eyeball these graphs, and figure out the critical values for every single different research question, because the critical values are going to change depending on what you're measuring, man, that sounds like a drag. That sounds like a pain. There has to be a way to do it more efficiently, where maybe there's something we could do such that the values don't change, such that the values are standardized. Hey, wait a minute. I remember standardization. That was something we could do to scores. We could turn scores into z-scores, and that standardized them. And so we could then, no matter what variable we were dealing with, we had scores that were interpretable. Now, those were raw scores. Like, those were individual people's scores. I wonder if there's a way to not standardize scores, but standardize averages. Indeed there is. So, to think about this question again, I need to find critical values that are more efficient. Sure. In this example, the critical values were 22 and 34, but let's say I'm studying IQ, where the average is 100 and the standard deviation is 15. Is the critical values going to be 22 and 24? No. Or what if I'm studying how much you love your dog on a scale of 1 to 7? Are the critical values going to be 22 and 24? No. So I need a way to have more efficient critical values. Critical values that are standardized so that no matter what question I'm asking, they don't change. And how am I actually going to determine the p-value? What if I wanted to figure out the p-value? How might I do that? Well, let's remember what standardization did for scores. Remember this equation over here? This was our z-score equation for people's scores. It told us how many standard deviations an individual person's score, how that was different from the average in standard deviations. And if you remember from the second exam, that was one of the questions. You calculated a score for somebody, and then you were asked to interpret it. And the correct interpretation was this z-score tells you how many standard deviations someone is above or below the average. So let's do an example. Let's say Jenny, hey, that's me, got an 80 on an exam. So my X would be 80. And let's say that the average exam grade was 100. Okay. So there we've got 80 minus 100. And let's say the standard deviation was 10. How I would figure out that z-score then is 80 minus 100, which is negative 20, divided by 10. And so the z-score is equal to negative 2. So now I have a standardized score for my score. Me as an individual human person, my z-score is negative 2. That means I did 2 standard deviations below average. I did not do so hot. But you don't even have to know how many points the exam was out of. You don't even need to know what I was even measuring. If I tell you I have a z-score of negative 2, you know that whatever I was measuring, I was 2 standard deviations below average. That's the beauty of standardization. So how can we borrow from the z-score? How can we borrow from the z-score? Well, just put that knowledge in the back of your head that this form of this formula allows us to standardize. So we don't have to, so the scores are always the same no matter what you're measuring, right? My negative 2 means I'm 2 standard deviations below average no matter what you're measuring. Now let's also refresh our memory of what the central limit theorem tells us. It tells us that we have an infinite number of sample averages theoretically. It tells us that an infinite number of sample averages will always be normally distributed. It tells us that if we create a null hypothesis sampling distribution where we assume that the null hypothesis is true, that our infinite number of averages will be centered on the original population average for the null hypothesis population. So 28 in this case. It also tells us that the standard error for that null hypothesis sampling distribution is going to be equal to 12 over the square root of 16. Because 12 was the null hypothesis standard deviation, divide that by the square root of the sample size, and you get standard error. So, how are we going to use this information? To standardize our sample averages, standardize our critical values so we can stop drawing these pictures. We have an efficient recipe for figuring out whether or not to reject or fail to reject the null. How are we going to do that? Well, what we're going to do is instead of transforming people's scores into z-scores, we're going to transform our sample mean, our x-bar, from a raw sample average into a z-statistic. So we're going to calculate a z-statistic, which is a lot like a z-score. This equation is how we standardized this person's x. My score of 80, we standardized into a z-score, which then told you how many standard deviations I was away from the average. Well, what do we know about the null hypothesis sampling distribution? The infinite number of averages, right, are going to have an average of mu. So now just like we could compare my score to this average, I can compare my one sample average to that known population value of mu. And then just like I divided by the standard deviation for the scores to turn my score into a z-score, I can divide by the standard deviation for averages, which is standard error, to standardize my average. So instead of turning my average into a z-score, we say I turn it into a z-statistic. But all I'm doing is standardizing. That's literally all I'm doing. And then this value that I calculate will tell me how many standard errors my one x-bar is away from that null hypothesis average. It's simply using the same kind of z equation. Instead of now calculating a z-score, we're calculating a z-statistic. Here we were standardizing a person's score. Here we're just standardizing that sample average. And so this makes it great because now that I've standardized, I'm dealing with a z-statistic, which is going to be a standardized metric. Just like z-scores were standardized, z-statistics are standardized. What we're doing is transforming this x-bar into something standardized called the z-statistic, which then becomes our very first inferential test statistic. Our very first number that we're going to calculate that allows us to efficiently and easily figure out whether or not we should reject or fail to reject the null hypothesis. So let's apply this to the current example. Here we've got the x-bar for our one sample, 30. Here we have that null hypothesis average, and we're going to compare 30 to 28. This is going to tell us how different 30 is from 28. But I don't want to know how different it is in raw units. No, I want something standardized, like the z. But now instead of z-score, it's called a z-statistic. We're turning 30 into a z-statistic by standardizing it. So 30 compared to 28, and then we divide by the standard error. 12 over the square root of 16, because remember, that was our original information from this problem, right? Let me erase all this stuff, right? This was our original example. Our standard error is based on the null hypothesis standard deviation, the known population average, divided by the square root of the sample size. And once you grab one sample of 16 kids, that means your theoretical hypothetical standard deviation of the mean, each sample is going to have 16 kids in it. And so this is our standard error, which as you recall turned out to be 3, right? 12 over the square root of 16 is 12 over 4. And so standard error is 3, right? And so then the bottom part of the fraction is 3. The top part of the fraction is 2, because 30 minus 28 is 2. 2 divided by 3 is 0.66666666 forever. So you can interpret this almost like a z-score, but it's not a z-score. It's a z-statistic. Instead of transforming a person's raw score, we've transformed this x-bar. We have turned 30 into something standardized, which is now going to be much easier to interpret. And you can do this for any average, for any variable, for any research question. You can plug your average into an equation like this, and it pops out with something standardized, which then you can use as a recipe to reject or fail to reject the null hypothesis. And let's see how we're going to do that. So what this did, us calculating a 0.666666, round that to 0.67, standardized your sample average. It standardized your x-bar. Ooh, my little x there is missing its little bar on top. I wonder how that happened. Sorry, let me draw that in there. It's supposed to be an x-bar. I lost my bar there. Anyway, so what you've done is standardize your sample average. We standardized 30. But what it also does is standardize your null hypothesis sampling distribution. It turns it into an infinite number of z's. And it's exactly like turning all the scores into z's, except now we've turned all of our sample averages into z's. They're not called z-scores now, they're called z-statistics. But we're now working with that z metric, that standardized metrics. And so if you think about it, z-statistics are to sample averages as z-scores are to individual scores. It's kind of like an analogy, but it's just like that. Z-scores are standardized scores, and z-statistics are just standardized averages, right? Where not only have we standardized the x-bar, but now our null hypothesis sampling distribution is also standardized. So we have an infinite number of sample averages that are all z's. And what do we know about the average of any set of z's? Well, the average will be 0. And the standard deviation of a bunch of z's is always what? That's right, it's 1. And so no matter what your variable, no matter what your variable, no matter what your research question, your null hypothesis sampling distribution, once you've calculated the z statistic, becomes a standardized null hypothesis sampling distribution. It becomes the standard normal distribution. You go from raw units that look like this, right? The null distribution. This is the null distribution in raw units that was centered on 28, where the standard error was 3, one standard error above 31, two standard errors above 34, one standard error below 25, two standard errors below 22. This was the null hypothesis sampling distribution that was for the raw units, because I was measuring academic performance, and the average for academic performance was 28. And here was 30 in those raw units, and here was 30. Now, the minute I calculate and standardize this X bar, I've also standardized the null hypothesis sampling distribution. And so voila, we have turned our X bar into a Z statistic of 0.67, but now my infinite number of averages on the null hypothesis sampling distribution are also standardized. And we know that an infinite number of Z's, or any set of Z's, is going to have an average of 0. So 28 has become 0. And standard error, it was 3 in raw units, but now it's 1. Because remember, standard error is just the standard deviation of the infinite number of averages, but these are now Z's. Z statistic, you have an infinite number of averages that are now Z's. And because they're Z's, their standard deviation, their standard error is now 1. So 1 standard error away is 1. 2 standard errors away is 2. 1 standard error below is -1. 2 standard errors below is -2. And so this allows us to standardize. The Z statistic standardizes our X bar and standardizes our null hypothesis sampling distribution. So we're dealing with the standard normal distribution. Table A1 in the back of your book, wonderful, hooray. We can now use that standard normal distribution to now wrap our head around the null hypothesis sampling distribution. And now we have critical values that won't change because we've standardized. So now we can use that Z table, right? Which has standardized Z values, remember? Because we don't want a different table for every raw unit. And standardizing, turning 30 into that calculated Z value of 0.67, right? Turning it into that Z statistic allows us to look up critical values in the Z metric. And we can actually look up the p-value now, if you want to, using that table A1, that Z table in the back of your book. Because that's what it's called. It's called a Z table. It's the table for the standard normal distribution, right? And that calculated value of 0.67, when I round, 0.666666 forever, that's how many standard errors 30 is away from 28. It's 0.67 standard errors. Just like but it's just a standardized value. It's a Z statistic, right? Our one sample of 16 kids were 0.67 standard errors away from that population value, from that null hypothesis population mean of 28, right? 30 was 0.67 standard errors away from 28. We've just transformed. We've standardized. We've turned things from the raw scores into the Z statistics. And so let's see how we can now do this, how we can look up efficient critical values that aren't going to change, because now they're standardized critical values. And let's use table A1. Here, we can, because we know that our infinite number of averages are just going to be a bunch of Z's, promise, the infinite number of averages are going to be a bunch of Z's, we know, and because we know, thanks central limit theorem, that an infinite number of averages are normal, those are the two things I need in order to use table A1. We know that the infinite number of averages will be normal. Now we've standardized, so now we know that our null hypothesis sampling distribution is going to be a standard normal distribution. A normal distribution of Z statistics. And so here we've got all the Z's. And let's figure out how we can use this table to figure out what our standardized critical values were. Now, our raw critical values were 22 and 34. Let's go here, right? When I chose a two-tailed test with alpha of 0.05, our raw critical values were 22 and 34, and I calculated those. That's not something you can do. I went ahead and looked up what the raw critical values would be. I calculated them, but you can just eyeball it. I'm telling you that this is 2.5% down here and 2.5% up here. And so then the upper critical value in the raw scores, the raw units, was 34. The lower critical value was 22 in the raw units. Well, let's see, now that we've standardized, how we can figure out what the standardized critical values would be, because then those be the critical values no matter what research question we're using, as long as we are doing a z-test. Well, what we can do is this. If we're doing a two-tailed test, what we're saying is in the upper tail, our alpha is going to be 2.5%, right? Or technically 0.025, because remember, alpha is a proportion. And so here we find the percent in tail that is for 2.5%. You remember doing this. We did this for people's scores. But now we're just doing this for the infinite number of averages. So I say, okay, I need the percent in tail that would say 2.5% of all the averages. Oh, there's 2.5%, right? The percent in tail, this would mean if the percent in tail is 2.5, that means this would be correspond to an alpha of 0.025, right? Because this is a percentage, and to turn it into a proportion, it's 0.025, right? And then I look over here, hey, look, it looks like the z that would cut off 2.5% is 1.96, darn close to 2. Because if you look here, that's about 2 standard errors away. And if you remember back, when we were discussing normal distributions, I told you that technically 95% of all the cases on a normal distribution would be within 1.96 above and 1.96 below, but it's roughly 2. But here we find then technically that critical z is 1.96. And I'll show you a picture of that in a second. But what this table is telling you to do is, if you're doing a two-tailed test, then the percent in one tail is 2.5%, because 2.5% is in the other tail, right? Let me draw that for you. Right, so here is my null hypothesis sampling distribution. Ooh, that's too thick. Here's my null hypothesis sampling distribution. And what I'm saying is I'm having a two-tailed alpha, right? 2.5% up here, 2.5% down here. Well, my standard normal table is telling me that if it's standardized and 2.5% is in the upper tail, then the z value that cuts off that 2.5% is 1.96. 1.96 is this number right here. And because z distributions or normal distributions are symmetrical, over here must be negative 1.96. And so let's look at a better picture than my chicken scratches, right? What this table is telling us, we're putting 2.5% in this upper tail, right here. 2.5% is in that tail. And so 2.5% is in this lower tail. And so they're telling you that the z value that cuts off 2.5% is 1.96. 1.96 here, and then negative 1.96 here. And so now we have standardized critical values, which means for any research question where you can do a z-test for it, you standardize that x bar, where you take x bar, subtract mu, divide by standard error. Your critical values, if you're doing a two-tailed test and your alpha is 0.05, is always going to be plus and minus 1.96. So if you calculate a z above 1.96, reject the null, because that's saying that your z statistic is in the area of rejection. If you calculate anything smaller or more extreme is the phrase I like to use, the negative 1.96, you're going to be in the lower area of rejection, which means your z-statistic was in the area of rejection. The beauty of the z-statistic is that you standardize. So your critical values are always the same as long as you have the same alpha and as long as you're doing a two-tailed test. And if you're doing a z-test, if you have an alpha of 0.05, that's what it normally is, and you're doing a two-tailed test, the critical values are always 1.96 positive and 1.96 negative. Calculate your z-statistic. You don't even have to draw a picture. Calculate the z-statistic, just like we did here. Let me erase my scrawls. Calculate the z-statistic. If what you calculate is more extreme than plus or negative 1.96, higher than positive 1.96, or smaller than negative 1.96, more extreme, you're going to reject the null. Period. Efficient. It's a recipe. So you can stop having to draw pictures. You just plug in the values, your sample average, your null hypothesis average, and here is standard error. If this number is more extreme than the now standardized critical values, which don't change, plus and minus 1.96, you reject the null hypothesis. If it's not more extreme, then you fail to reject. And here you can see 0.66 is not more extreme than our critical values of 1.96, plus and minus 1.96, because this is a two-tailed test. Positive 1.96 is one critical value, negative 1.96 is the other critical value. This was not more extreme, so fail to reject. That is the beauty of the z-test. It standardizes your life for you, right? And if we then look at this example on the standard graph, here we see we've turned x bar into 30. X bar was 30. We standardized 0.67 into 0.67. So we turned this raw metric into 0.67. And so now we're dealing with this standardized value. And so where is it on here? Where is 0.67 on here? Right here. Z equals 0.67. That's where 0.67 would be, right? Right here. Not in the area of rejection, not more extreme than the critical value, failed to reject the null. And that's the whole idea behind this approach. Now, we can also use the z-table to calculate p-values if we want. And we just work backwards. Here, you would find your z-statistic, which again was 0.67, on the z-table, and then you find the percent in tail. And here I see that the percent in tail is 25.14 for the z-statistic of 0.67. Now remember, we've just standardized 0.67, right? 30 has become 0.67, and so the percent in tail is 0.25, right? Percent in tail is 0.25, but again, this is a two-tailed test, and so this is also p, and so we add them together to get a p of 0.5028, because I see a z-statistic of 0.67, the percent in tail is 25.14, that becomes a proportion of 0.2514, so then the p-value is 0.5028. Now, you are never going to be required to use this table to find p-values, because once we move away from z-statistics, we won't be able to use table to find p-values. But I just wanted to show you that at least for the z-statistic, you could use table A1 to do it. You could. We are not going to do that. Rather, we are going to look up critical values. So make sure you understand how I arrived at these critical values of plus and minus 1.96. Right? Make sure you understand that because I chose an alpha of 0.05, I found 2.5% in the tail. This told me that the z that corresponds to 2.5% is 1.96. So now I've got my two-tailed alpha, 0.025 in here, 0.025 in here. So my upper critical value becomes 1.96. My lower critical value becomes negative 1.96. And here's my z statistic. Not more extreme than the critical values, failed to reject the null. right? That is the approach we're going to use on the upcoming exam 3, which is a while from now, and you may in fact be required to look up critical values. You're certainly going to need to look up critical values on your 3rd lab. So make sure you understand how it arrived at these critical values for the Z's test. So what do these numbers mean? So we've calculated a Z statistic of 0.67. So Z equals 0.67. That's just a period, but I don't like it there. It makes it confusing. And then I went ahead and looked up the p-value for 0.67. And that p-value was 0.505, right? So what does all that mean, right? Well, the p-value means there's a 50-50 chance, right? A probability of 0.5028 of getting a sample mean of 30 or more extreme. So the p equals 0.5028, right? Is the null a reasonable thing to believe? Absolutely. Absolutely it is, because that's a big probability. It is very probable that we would have gotten a sample average of 30. 30 is super probable, right? And remember, the p-value is the probability of getting a sample like yours if the null is true. In sort of put in everyday language, the p-value is the probability of seeing 30 simply due to chance. There is a 50% chance, a probability of 0.5028 of seeing something like 30 just due to chance. Well, then I can't reject the null. I have to stick with that boring null hypothesis. Head Start doesn't work. And so notice that this p-value was bigger than alpha. Notice that our Z statistic of 0.67 was much less extreme than our critical values of 1.96. And they're telling you the same story, because big statistics come with small p-values. And small statistics, like 0.67, because Z is our first inferential statistic, the Z statistic is an inferential statistic. Our small statistic of 0.67 came with a big p-value. Because remember, p's are probabilities. They range from 0 to 1. And 0.5, that's like a 50-50 shot, right? Half the time you would have seen something like 30. Fail to reject. And so and these two ways of making a decision will always tell the same story, right? So in practical application, you're going to calculate a Z. It's like a recipe. You just plug it in. X bar, mu, sigma, n. Subtract the sample average from the population average. Let me write that. Oops, sorry. Let me write that equation for you again, right? The Z equation. X bar minus mu divided by standard error. That will give you your Z statistic, right? Once you calculate it, which we did, 0.67, you can compare that to the critical value. If what you calculate is bigger than the critical value, you reject. But if what you calculate is smaller, and it totally is, then you fail to reject the null. And that's what happened here. Or let's say you're using a computer program and it spits out a p-value. It says, oh, your sample data, your Z statistic, it's got a p-value of 0.5028. Well, you can compare the p-value to alpha. Because remember, these are areas on that null hypothesis graph, right? Where the whole thing is 1. We're figuring out probabilities. 0 to 1. There can be nothing bigger than 1. Our p-value was 0.5028. That was much bigger than 0.05. And when your p-value is bigger than alpha, you fail to reject the null. If your p-value is smaller than alpha, you reject the null. Now in this case, our p was bigger than alpha. Because again, small statistics are highly probable if the null is true. Small statistics are probable, so they come with big p-values. Large statistics are improbable if the null is true, so come with small p-values. And we are going to use the critical value approach. We are going to calculate our Z statistics and then compare them to our critical values. Does that mean you're never going to have to answer questions about p? No. But you will, you're not going to have to calculate them. But you know for sure that if you calculate something smaller than the critical value, you fail to reject the null and p is big. P is greater than alpha. If you calculate something bigger than the critical value, which we did not do in this case, you're going to reject the null and P will be smaller than alpha, right? There will be no exceptions to this rule. Literally no exceptions to this rule. If what you calculate is big, bigger than what? The critical value. Reject the null, P is less than alpha. If what you calculate is small, which is what happened here to us, smaller than what? The critical values. You know you're going to fail to reject the null and P will be big, bigger than alpha. That is what you'll need to know from here on out, because we're not going to calculate p-values. Do we need to know about them? Sure. But what we need to know is simply, is our p greater or less than alpha? That's what we need to know. And we know if our z statistics are big, reject the null. P is small. Our z was not big. Oh, our z wasn't big. Not bigger than the critical value. Failed to reject the null. P is bigger than alpha. P is bigger than alpha. And the nice thing is there are no exceptions to this, right? This is how it works for every inferential test we're going to do from here on out. Big statistics, reject the null, P is small. Big Z statistics, which we did not get here. Small statistics, like small Z statistics, fail to reject the null, P is big. Right? Every statistic we're going to do for the rest of the semester is going to work just like this. So that's nice. Consistency at last. So, a couple of things I want you to keep in mind in the back of your head, right? In order to do a z-test, you got to know some stuff. You got to know some stuff about the known population, right? You have to have a comparison population with some known values. Because let's write the equation for the z statistic over here. The z statistic is calculated like this. Z equals, z statistic now, not score, is your sample average x bar minus mu, the null hypothesis mu, divided by standard error. So, what do I need to know about the comparison population before I collect any data? If I'm going to do a z-test, what do I have to know about some comparison population? Well, I have to know mu, right? What else do I have to know about that known population, that null population? I got to know sigma. So what numbers are going to come from your actual sample, though? What numbers are going to be generated by your actual sample of people? Well, n, right? Sample size is going to, your one sample of people is going to dictate how many people are in your infinite number of averages. So n from your actual sample is going to go into this z statistic and x bar. So these four ingredients, if you know them, if you've got a mu, if you've got a sigma, if you've got an n, if you've got an x bar, these are the four ingredients that you need for a z statistic efficient way of rejecting and failing to reject the null hypothesis. Plug it in and compare it to the critical value. If what you calculate is big, reject the null like the lemon hypothesis that you want to reject. If what you calculate is small, you're sad. Failed to reject the null. Couple other things. And so the beauty of the critical values is that they don't change. They don't change. Here is the critical values for any two-tailed z-test where alpha is 0.05. They're always positive 1.96 and negative 1.96. And so if you calculate an average bigger than 1.96, smaller than negative 1.96, either way, you're going to reject the null hypothesis, and p will be small. P will be less than alpha. But what if you're doing a one-tailed test? Well, if you're doing a one-tailed test, then you're only going to have one critical value. And so I just want to point out that the critical values aren't always plus and minus 1.96. They're just always plus and minus 1.96 if you're doing a two-tailed test and alpha is 0.05. And alpha is normally 0.05. But let's see what your critical value is if you're doing a one-tailed test. Well, remember in a one-tailed test, you put all of your alpha in one tail. All alpha of 0.05 goes in one tail. And so here we have only one critical value. And let's say you're only looking in the upper tail. Well, then it would be a positive critical value of 1.64. Let's see what that looks like. So here, all of alpha goes into this upper tail. And so the critical value is 1.64. And you only have one critical value. If you calculate anything above 1.64, you reject the null. But anything down here, and you fail to reject. Right? And that's how you can use table A1 to look up any critical value. And let's say you want to change your alpha. Let's say instead of an alpha of 5, you want to use an alpha of 3%, 0.03. You can do that. Here you go. Here's an alpha of 0.03. 3% would correspond to an alpha of 0.03. Well, here's your new critical value because you've changed your alpha, right? And so this table can be used. The percent in tail stands in for your alpha because that's what alpha is. It's the percent in the tail, right? And now you can look up your standardized critical values. Beautiful. Thank you, table A1. And so let me work through a crazy example for you to try to get you to wrap your head around what the Z statistic is. So let's calculate this crazy example. Is the average IQ really 100? Because let's say I decide to take one of those BuzzFeed internet IQ tests, right? And I say, well, I wonder if they're doing the same kind of IQ test that they do in like the psychologist's office. And so I right away I email BuzzFeed and I say, hey, BuzzFeed, you know those quizzes that you give people? What's the average IQ for a sample of your people who take your IQ test? And so they say, well, the last sample of people who took it was 225 people, and they got an average of 100. An average of 10. So my one sample of 225 quiz takers had an average of 10. And I'm curious if this is the same, if this sample of BuzzFeed IQs is the same as what I know the population IQ is based on standardized assessments, which like legit psychology assessments. So let's say I know ahead of time that the population average is 100, like not BuzzFeed IQ, regular assessed IQ in like a psychologist's office with a standard deviation of 15. And I'm curious if my one sample of BuzzFeed IQ quiz takers who got an average of 10, if they're the same or different from this known population. So let's calculate my Z. I'm going to move this equation over here. So let's calculate my Z. I'm going to standardize that X bar of 10. So let's do it. 10 minus 100, because that's the null value, right? Does 10 come from the same population that has an average of 100 is what we're really asking. And then I get sigma, which is 15, divided by the square root of 225, because that's what I know my infinite number of averages are going to have 225 people. Well, the square root of 225 is 15. So I end up with, and then 10 minus 100 is negative 90. So I end up with negative 90 over 15 over 15, right? So 15 over 15 is 1. So I end up with negative 90 over 1. So my Z statistic is negative 90. Whoops. When you work out all this math step by step, the Z statistic is, for this problem, negative 90. Negative 90? That's crazy. So a Z of negative 90? 10 is 90 standard errors away? 90 standard errors away? Yeah, so what would that look like? Oh my goodness. On a theoretical, hypothetical sampling distribution of the mean. Okay, so now we've standardized. Hooray! So my theoretical, hypothetical sampling distribution of the mean is normal, which we know averages will always be. But now it's centered on 0. Hooray for standardization. It has a standard error of 1. So where would negative 90 be? Oh no, I don't have enough screen to do negative 90. Oh no. Oh my goodness. Oh my gosh. Oh my god, I'm going to have to keep drawing. Oh no, there goes my graph. Wait, where's my graph going? Oh no. Ah! right? Oh my goodness. Oh my goodness. Negative 90 would be like somewhere over here in extreme land, right? And if my critical value below here is negative 1.96, is negative 90 extreme? Why, yes, it is. This is definitely in this extreme area of rejection. Whoa, that is way below the critical value. Reject the null hypothesis. Negative 90 is super improbable. Oh my goodness. And absolutely it is. Negative 90 is super improbable. So the p-value would be teeny, teeny, tiny. So I'm guessing these BuzzFeed quiz takers do not have an average IQ of 100. Probably something much closer to 10. Reject the null hypothesis. And P would be teeny, 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 tiny. The p-value for a z of negative 90 would be teeny, 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 tiny. Because big numbers are super improbable if the null is true. And that's the beauty of the z-test, is because now it allows us to efficiently reject and fail to reject the null. Right? And so one more time. Once you've calculated your z statistic, what are you going to do with it? You're going to compare your calculated z to what's called the critical z value. That it's a critical value, but now it's called the critical z value. If what you calculate is more extreme than the critical value, farther away from 0, right, then you reject the null, just like we did in the last example. Negative 90 was way more extreme than negative 1.96. Reject the null, right? That will mean the p-value must be smaller than alpha. And when p is smaller than alpha, you reject the null hypothesis. These are just two different ways of thinking about the exact same thing. And that's the z-test. It's the culmination of everything we've learned so far. Our very first inferential test. The null hypothesis significance test that we learned about last time, standardized. So that our critical values are standardized, so we can stop drawing pictures. You calculate the statistic, the z statistic, compare it to the critical value. If what you calculate is big, reject the null hypothesis and have a party. Go on Oprah. Talk about the answer to your research question. Right? All right, thanks very much, guys. Next time, we'll talk about confidence intervals, which is all the same information put together in a new way to do something a little different. See you next time.